Alright, time for another DraftPhysics.com video presentation. So this is an old 60 symbols video on energy, and it's just so bad. They just haven't got any kind of clue at all. So I figure, first I shall explain the simplicity of what the universe could be. I would certainly assert this is exactly how it works pretty much. And it's easy to follow along. So Descartes was pretty much the first to sort of write about conservation and the idea that the universe was put in motion and that the motion in the universe is just going from one object to another object. Basically arguing it's a push universe. Now, I don't think he exactly said that, but that's what it comes down to. So the idea is the universe is full of stuff moving in all directions. That's the stuff we call force. It's the energy in the universe, and it's free. It's flying free, and it pushes on everything. Okay, so everything gets hit with stuff heading right for it. So in a universe full of stuff moving in all directions, there's a certain number of stuff, a certain amount of it, that's going to just head right for me. Okay, and it's going to seem like I'm just getting hit by that. Because the rest of the universe is going to be irrelevant, because it's not going to interact with me. But the parts heading for me are going to hit me, and they're all going to hit me even from all those sides, and I'm just going to get pressurized by that fact. I'm going to be compressed. So that's the E equals mc squared part. That's the part where everything's under pressure. So anything material is under pressure. And the idea is that all I have to do is have a differential in that pressure, and the differential will cause me to move. So a few more extra bits of energy hit me from one side than the other side, then I start going that way. Because I essentially collect these things. The extra bits stick. I mean, you can't get rid of them until some extra bits come the other way and unstick me. Now, this creates a circumstance of drag, which is kind of complicated and has to do with the fact that electrons and protons are in arrangements, and so drag has to be defeated by more complex matter. Elemental electrons and protons can't overcome drag, and they are in fact dragged to a halt. You can't shoot an electron from, say, the space station to the moon. Even though it's supposed to be pretty empty space, pretty good vacuum, can't do it. You won't get there. Alright. So, I'm not going to get into that subject. So the idea is that chemical energy is just really the same kind of, it's just pressure. And what happens is you can have atoms that can get close to each other, okay, because of their polarization, because of the arrangement of the electrons and protons, their magnetism, so to speak. And then you can add another compound, another element, and they'll stick to each other, and that becomes a bigger object. And so in a sense it expands out into the environment and pushes on the other stuff because it's expanding. So the electrons are repulsive, and the nature of repulsion is basically just saying, yeah, there's always pressure between things, and the fact is if they're moving towards each other, okay, there'll be a braking, a capacity to slow them down, based on the fact that there is actually energy that's going to keep reflecting as they keep moving towards each other. And so the same piece of energy will keep saying stop, 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 pushing until they stop. And then that energy will disappear and wait for some new energy to cause them to move in some new direction. So the stopping force is basically built into the function of electrons. But again, it doesn't do it for free. It's all conserved. Every arrow in the universe, every little bit of force has a history. It has billions of years of history. It's been doing the same thing, pushing on things and just being thrown off and thrown in, thrown off, thrown in. It sticks to something and moves it, and then it goes free into the universe again, into the field of pressure, until it hits some other thing and moves it for a while. And so every bit has had a history. Anyway, so that's the simplification. It's just a mechanical function of the universe. There's little bits moving the speed of light. They ultimately move electrons and protons. And the electrons and protons, when they're moved, move the atoms. And then the atoms, as an object, get moved. And it's all just about collecting pushes. little bits of stuff that are pushing. And if you have more pushing from one side than the other side, you go with the side where there's more pushers. And so instead of that simple description, they've chosen this much more ambiguous and nonsensical, plainly, description.
So if I bring him up to here, he just has potential energy and he's not moving, so there's no kinetic energy.
So potential energy doesn't really mean anything. There's potential circumstances. Now, potential energy means something in terms of dynamite or some pure element that you're going to oxidize. So the idea is that the oxygen atoms will hit the compound, they'll combine with it. The oxygen atoms become bigger because of the bit you added. They're expanding. They can't be compressed. They take up more space. And so that becomes an explosion because it happens so fast. There's so much of it happening. And all of that stuff has to be repelled by the electrons and pushed out. But it's kind of always in storage in one way or another. It's like a piece of popcorn. You're just creating a circumstance where the energy is sort of stored in the popcorn, in the sense that if you can heat the little bit of water on the inside, you can cause the whole thing to explode. So it's not coming from the popcorn, it's coming from the energy, the heat that you're putting in, but the idea, okay, that there's a circumstance that allows for a great deal of pressure to be built up. But chemical energy isn't mysterious energy. It's the same energy. It's the same pushing of electrons and protons and creating arrangements that are like a spring where there's a great deal of potential for them to fly away from each other if you just change their environmental circumstance a little bit.
And as I let him go, he swings backwards and forwards between the same places, more or less.
Right. Now you could do the same thing in a stream of water. You could create a pendulum, okay, an object, and you give it motion, and you get a similar kind of effect, in the sense that that motion will stay in that system and it'll create turbulence and do its little thing, because the energy is not nothing. It's not from nowhere. The fact is every object sitting here on the surface of the earth is in a stream, a constant stream of force. And that force is real. It sticks to objects, they acquire it, and they're changed by it. They're internally changed. So if I throw a wrench in space, that wrench is physically different than when I don't throw. It's different. It's been affected by force. It has force stuck to it that caused it to arrange differently, and that's why it's still moving. It's moving.
So big E is the symbol that gets used for energy, and it sort of crops up all over the place in physics, probably in the most famous equation of them all, E equals mc squared. The E,
which doesn't mean much, frankly. It doesn't say much. It's just this preposterously large number, the speed of light squared. And you're just saying that, yes, there's that much potential in any material object in the universe that, in a sense, the pressure of the field is the same for every object. I mean, the density of it, the bigger you get, the more of it you're absorbing. The smaller you are, the less of it you're absorbing, because you're taking up less space. There's more arrows going to hit you the bigger you get. Just a fact. So that's the correlation. It doesn't need to be complicated.
and that is the energy of something.
It's just something which is always conserved, so it's either nuclear.
So that's the important part. So it's something that's always conserved, and yet they don't have any explanation for the something. I mean, if the substance, essentially, you can just argue that it's obviously some kind of substance. You don't conserve something that isn't a something. You can't conserve a nothing. You know, it's only a something that you can have to worry about where it goes. You know, you don't conserve ghost. You know, you could conserve the number of people.
Nuclear energy, energy associated with mass equals mc squared.
So he says the same crap again. So it's not associated. It's associated with mass, But again, the real point is that's the pressure that you're going to understand everything is in. That's why gravity is a consistent force and other things are consistent. It's because, yes, it's really just about your profile. It's about how many electrons and protons you have will decide how big a profile you have, and how big a profile you have will decide how much energy you collect.
It's energy associated with thermal motion, or it can be an electron.
So again, thermal motion is just electrons and protons moving. So again, it's just momentum within the chemistry of the electrons and the protons. So thermal isn't any different than chemical, and it's really just storage in the form of arrangements between electrons and protons. So it's all kind of magnetic. Magnetism and charge are essentially the same thing, and so it's built into the fact that electrons and protons can be both attractive and repulsive. So all I have to do is turn magnets, and all of a sudden I create a bunch of pressure. So just take two magnets that are pulling towards each other, just reverse them, and they'll fly apart.
Magnetic field. It can have many different forms.
Causes or forms. It's all the same thing. There's only one universe. It's the small universe, and it's a push universe. So I could say those two things, those two concepts. And I guess that's just too challenging if I was to make that argument to you. That yes, these are facts that'll never change. It's a push universe, and the only universe is the small universe, the one with the electrons and protons in it. Everything that happens there first. If the electrons and protons aren't doing it, then the thing that's made out of them isn't doing anything. It all happens in the smallest micro universe.
But if you add all these things together at each stage and keep the bookkeeping, it is that quantity which is always...
So keeping the bookkeeping of just forming some silly equation that puts two inverted elements. You know, you do this with frequency and frequency and wavelength. They're two inverted numbers. So you can just create a formula that has frequency in this one and has wavelength in this one. And it'll always be balanced because you're using the inverse of the other thing on the other side of the equation. So I mean, it's just game playing to talk about systems like springs that, of course, you could argue that as you're pushing in on the spring, the one object's losing energy and the spring is collecting it. But that's not how they think about it. They think about it in some sort of, you know, like it's a potentiality or something, when no, it's real. You've really disrupted the spring. Spring's in a new condition, and the new condition is work was required to create the new condition, and you just applied the work, created the new condition. The new condition now can give the work back.
Conserved, but I'm not going to tell you what it is because it's one of those deep mysteries.
Deep mystery. So again, you know, does it really seem like a deep mystery? It doesn't seem like a deep mystery to me. Never really seemed all that mysterious. As soon as, like I said, as soon as they say the word conserved, well, you know it's a something, and then you're just saying, well, what's the something doing? Well, basically, the idea is you can understand it's just two choices, push and pull, and we know pull doesn't make any sense because I can't just. An electron doesn't have arms. I mean, it can't pull on something. And even if it were to pull on something like a doorknob, it's not really pulling on it. It's going to push on the back side of it. So again, you're just back to, it's a push universe.
If one of your kids said, "Dad, what is energy?" how would you answer that?
That's a tough question. What is energy?
I mean, that one's just so simple. You just say motion. Right? I mean, why is this complicated? All the forms of energy all have something in common, and it's motion. Stuff has to move. So matter moving seems a pretty good explanation of trapped energy anyway. And then when you want to talk about the free energy, you know, you can just point out that, yes, there's two states that a piece of force can be in. It can be in the state where it's pushing a piece of matter, or the state where it's flying free. That's it, two states.
Have you got a dictionary, George? I've got one upstairs.
We'll look it up another day.
Okay.
You see, it's how much oomph something's got, but that's not really a very scientific definition, is it, really?
No, you just made it up anyway, because that's not going to be in the dictionary. Anyway, so they really ruined the word, right? Because the simple thing to say would be momentum, right? But no, that won't come out of their mouths. And 1/2 mv squared certainly doesn't say anything reasonable.
Energy comes in many different forms, and
So again, it's really just one form. It's electrons and protons moving. That's it for us. You can't see energy in any other way than when it interacts with matter. So when it's not interacting with matter, it's not doing anything. It's completely inert to existence. You can't see it, you can't know about it, you can't detect it, you can't do anything. You have to make it move matter for us to give a damn. And that's it.
the normal ones we talk about are energy due to motion, which is called kinetic energy.
So another silly thing, okay, so we know motion is momentum, so again, why have this word duality problem? Just makes a horrible mess. And their kinetic energy formula is actually made out of momentum, so the momentum obviously has to come first. The mv part is in 1/2 mv squared. So you have to pay attention to momentum because it's inside of your own formula. And that's sort of the giveaway that, you know, the kinetic energy has got to be kind of fake because it's just a mathematical reason. That square term basically dictates that every time, you know, you do a conversion between a light object into a heavy object, you're going to lose kinetic energy, and every time you take the energy, the momentum from a heavy object and put it in a light object, you're going to gain extra energy.
And energy due to position, which is called potential energy.
So again, it's, you know, it's a really bad terminology. The distinction between something active and something passive, that is storage, and something that's active. That should be the difference. The compressed spring versus the relaxed spring kind of argument, to recognize this, because potential is always in the form of something that you can find where the tension is. You can find where the pressure is that can be released. You can find that it's a dam and you can, you know, you've got the water in the reservoir. You had to fill it up in a lot of cases. You had to actually put the water in the reservoir so you know there's something in there because you put it in there.
So there are all these different kinds of energy. There's kind of an exchange rate between them, so you can actually interchange. You can change your potential energy into kinetic energy by dropping something, for example. So they are all really the same thing.
So there's no point in saying they are the same thing if you don't get to the point that, well, they're all a manifestation of the fact that there's energy filling the universe, and there's places where, you know, you can be affected by the movement of that energy, and gravity's that case. Gravity's a stream, and you can throw something into the stream and watch it get moved by the stream. But it can't be moved if there's a waterfall, or, you know, the stream goes into a tunnel or a pipe or something. I mean, some circumstance where you understand that your capacity to absorb its energy is limited, and once you hit the Earth's surface, the force can't keep pushing you.
But it's just stored in different forms. So you can have the chemical energy stored in a battery, for example, which you can then turn into kinetic energy when you plug that.
So it's in the form of kinetic energy in the battery. The battery is very full of action, so to speak, in terms of its potential. And you've compressed a bunch of springs, and you're just saying, well, you know, I can pull the trigger and release what I've compressed. So it's, you know, it really is storage. Potential energy is stored energy. But in the case of like gravity, it's obviously not stored energy. It's the nature of the universe that there's a constant flow that you can take advantage of. But it's not free, because to put it in the position upstream, you have to paddle upstream before you can let the boat get pushed by the stream. You have to move against the wind to be pushed by the wind.
battery into a motor.
And so I touch here, this is just a battery, there's a magnet down here, and as I touch it, it spins round like mad. And as I leave it, you'll see it's not a perpetual motion machine unless I leave the electrical contact. It slows down and comes to a stop. So if you're a child on a swing and you...
So this is a really poor example because, the dynamics of a swing are a little more, it's a little complicated in terms of what you're doing to add energy to your motion. And so, there's so many better examples of storage versus releasing energy and this whole potential thing. So the only thing you're changing when you raise something up against gravity is the fact that you have to use up something's energy to gain that position, and gravity just keeps giving it back. I mean, the fact that the gravity absorbs the energy in the object and brings it to a stop, and then it's stopped in a position where it can't fall straight down, so it has to swing. It has to convert the energy going down into energy going sideways.
Move backwards, that's energy due to position, but if you let it go and it moves, that's energy due to motion. So I'd like you to imagine, now this was given to me by my son for Christmas. It's very strange when you're a physicist what you get given for presents.
Given to you by your son, okay. I think that's what he said.
At Christmas, but this is my Albert Einstein doll, complete with a bit of chalk.
So interesting.
Do you think when you were given that?
I mean, this is what they're wasting. It says right here, it's one of the most important concepts in physics, and he's wasting time playing with a doll.
I had to say how wonderful it is, and he's going to be watching this. It was wonderful, Peter. Anyway, imagine Einstein is a pole vaulter, and he's charging along with this meter rule, pretending to be pole vaulting.
So all of this, instead to just talk about a spring. And so they never really talk about the tension in the pole, and that's all you're doing. You're transferring your motion. You're going to transfer it into the bending of the pole, which is going to stretch the atoms, which is going to pull the electrons and protons further away from each other. And they're dipoles. They're magnets. They want to stay close to each other. And so you're basically just going to stretch some of them, and they're going to say, I'm going to go back to my more comfortable position as soon as I get a chance, as soon as you take the pressure off.
And he comes all the way along to the little place where he puts it in the hole, and this gets bent.
Puts it in the hole.
Bent and bent. And now all the energy, his kinetic energy of motion, has been turned into bending energy of this rod.
Right, and you would say that you have to get it back, so you have to conserve it. So a catapult or something else has to conserve the mv, right? The motion, the mass, and the velocity has to be conserved, not the ke. All right, and so this would have been their opportunity to make some distinctions between momentum and kinetic energy, but they didn't bother.
And then he comes up as this unfurls, and he now just has potential energy due to his position. But being Einstein, he was the wrong way round. He should go over feet first, and there would be a rod and he'd fall down.
So that was just a terrible example, because obviously the pole vaulter is using the poles bending just to go straight up, essentially. Pole vaulters don't really shoot forward, they just go straight up.
So that's one example where you're converting kinetic energy of him sprinting as fast as he can to get as much kinetic energy.
So again, it really doesn't have anything to do with kinetic energy. It has to do with momentum, and he takes his momentum, his mass, puts all of that weight into this little pole, bends the hell out of it, okay, and the pole slowly gives the energy back, and he takes advantage of that to change direction. So he takes his forward motion and converts it to up motion.
Into potential energy of this bending of the pole.
So his speed, his velocity, running down the track is essentially showing you. You're seeing, the pole is letting you see it as motion, how much work it really can do. So his forward motion is being converted into pretty much just jumping. And this is how high you can go with that much speed. If, the limitations of your body can't do it very efficiently, where the pole can. You can't just jump.
Into potential energy due to his position.
So again, it's not his position, it's just the fact that now he can free fall. He's thrown himself off the surface of the earth, and now there's a distance he can free fall. And that's his, his potential changes, because all I have to do is keep lowering the thing he's falling on. So I keep lowering the surface. Like I say, if he was pole vaulting, it was going to land on an elevator, and the elevator was going to start going down. All of a sudden, I'm changing how much potential energy he has because I'm lowering the surface of the earth. That doesn't make any sense. So clearly, the potential is just to be in the stream of gravity and to have time to fall in that stream. And that's all it's going to be about. So he's entering the river, and the height just has to do with the fact that it's a known distance. Okay? And you're just going to travel a standard amount of distance in a standard amount of time, and it's the time that's going to dictate how much energy he's going to collect as he falls. So all of his potential is just in the amount of time he's going to have to fly in the stream, to go boating.
And if he's very clever, he can distort himself into such a shape that he gets his feet over first, and then his legs, and his arms go up in the air.
I mean, this is a kind of a bizarre way to explain energy, right? I mean...
And he can manage to get over, even though his center of gravity is below the bar. Another example for Paul...
So he has to add energy to the system. So essentially, he has to straighten his body. So he has to add that extra to get over to add a little bit of extra to get enough height to get over the bar.
Mr. Einstein, I'm going to put him on a swing, because when I was a child, I never knew how to do the swing properly.
So you can just imagine this child. So mommy had to teach him everything, apparently. Oof.
And my mother always had to push me. And so I'm going to fix him up so his fingers...
Yeah, you just would be like, well, I don't think you should tell anybody that story. Poof. A swing was challenging? Wow. I wonder what else you had a problem doing all on your own.
And toes are all wrapped around this properly, and we'll let him swing.
So this is just such a, such a wasted time.
So if I bring him up to here, he just has potential energy and he's not moving, so there's no kinetic.
So it's just about how much time he's going to have before he reaches a point where essentially he's going to hit the earth, in the sense that he's not going to be able to fall anymore. So he gets to fall a lot as he's going down the curve, but then he doesn't get to fall anymore at all. And it's just about that time. So the further out you go, the more time you're going to get. And the more time you get, the more velocity you get. So the longer you're getting pushed by the stream, the more energy you'll collect. I mean, that's... I hate to say it, the obvious correct answer.
Energy. And as I let him go, he swings backwards and forwards between...
Right, getting energy, losing energy, getting energy, losing energy, getting energy, losing energy, going upstream, going downstream, going upstream, going downstream, because he's stuck on a rope.
The same places, more or less. But if you notice carefully, it's slowing down. It's slowing down. It's not coming back as far as it did before. The result of the movement of Einstein through the air, and there's some friction and dissipation of energy.
And the bearings, right. So you can eliminate all this stuff, and, theoretically it should just keep going and going and going, but you can't eliminate the friction. Some points of friction are uneliminatable.
Here, it's all potential energy, and there's nothing else.
So there's no potential energy. There's gravity, a constant stream, and all you're saying is how much time am I going to give him flowing in the stream? And the more time he has flowing in the stream, the faster he's going to go.
Here it's partly kinetic because he's moving, and he's reduced his potential energy. The sum of the two is constant.
So it's just playing a game. The sum of the two is constant. It's just another way of associating those two different things, that you're changing the position. You go up the stream, then you go down the stream. You go up the stream, you go down the stream. Well, if you give down the stream a number that's inverses to your losing energy, then yeah, you're just saying, yes, they're always the same amount. I only have 10 pounds, whether I move it up and down 5 pounds here, 5 pounds, it's always the same 10. One of them gets weaker, one of them gets stronger.
It gets down to the bottom, it's all kinetic energy and there's no potential energy, and the sum is constant.
So again, it's not that there's no potential energy, in the sense that there's plenty of force acting on them, but now it can't do anything because it's all in these ropes. It's all being grounded. He's really sitting on the ground now.
Constant, apart from this little loss of energy due to friction. And then it goes up, and there might be some rocking motion that he does, but if you take account of all sources of energy,
so there's no conservation of all sources. I mean, obviously the energy is leaving Einstein, and he comes to a stop, and then he has to build it back up again.
And the total is fixed. This is the law of conservation of energy. It means that if you do the accounting properly...
Right, but it should be understood on a bigger scale that the conservation is a thing, a substance, and you're conserving it. So you're either letting it back free, or you're storing it, or it's always somewhere in the universe. So if you have more of it on the outside, then you have more pressure, pushing. If there's more of it on the inside, then there's less pressure on the outside. I mean, not complicated.
And you add up all the terms, mathematically, and then put it as a total. As the time varies, this remains constant, and it seems to be one of the most fundamental laws of nature.
It doesn't really work. So, that's where they get into this whole kinetic energy thing. Again, the formula says I automatically lose half the energy, disappears from the known universe every single time I convert, even splitting objects. I take the energy and I take it from one object and I give it to two objects. I'm going to give the two objects half the velocity, and because it's a squared v term, the velocity is squared, I've now obligated to say half the energy disappeared. So that's how unconservative their theorem is that it makes kinetic energy and it destroys kinetic energy all the time. If I do the inverse, I throw two balls in. They all weigh the same mass. I have three balls, one here, one here, one here. I shoot these two in and I put all the energy into one ball, leaving. It's going to leave with twice the velocity. It's now going to have twice the energy of what went in. It's going to have 4 times the energy of one of those objects. So I made free kinetic energy. It's nonsensical.
Energy is conserved.
There's an old unit of energy called an erg.
Who cares? So this is another part where you see, why are they talking about this irrelevancy? It really it doesn't connect to anything. There's an old unit called an erg. So why didn't he just first say, well, physics really screwed up because we have about 35 different ways of saying energy. We have calories, and then we have watts, and we have this, and we have all these different ways of measuring the same quantity.
Which is actually 10 to the minus 7 of a joule, so a 10 millionth of a joule. And for some reason, astronomers insist on holding on to it. It's a unit which the rest of the world threw away decades ago. But for some reason, many astronomers insist on continuing to measure their units in this. And an erg is a pathetically tiny, it's like the kinetic energy of a gnat or something. It's some pathetically small unit. So it's completely ridiculous for astronomy, but for some reason, just sort of lost in the mist of time now. It's a unit that astronomers insist on keeping on using.
Well, a joule isn't all that spectacular either, frankly. I mean, it's the amount of energy a stick of butter has when you drop it 1 meter. It's not a great standard either.
Now talk about how kids at school could get this thing to rock backwards and
So the whole erg thing didn't mean anything, right? It's just thrown in for no good reason. Just a complete waste of time.
forwards. I could never do it. You can either stand up on here or you sit down on your stool, and in one part of the cycle when it's coming back,
So all you're doing really is you're using your body, muscular, to push. So you're pushing your mass to a new location. So by lifting your feet or lowering your feet, you're basically just saying, I'm going to elevate my mass at the right point, and now I have more mass that's higher. And then when you're at the low point, you want to do the opposite, to reduce your profile.
you tuck your legs under, and when you get to the other part of the cycle where it's going forward, you lean back. And as a result of leaning forward, you lower your center of mass. In other words, where you're heaviest, which is around here.
That's really not what you're doing. You're moving your feet. Okay, it's really just about moving your legs and changing where they are in proportion to your center of mass. So as soon as you change where your legs are, you automatically raise your center of mass.
You lower it down, and when you go the other way, you're lowering it down. So you're changing effectively the length of the pendulum twice in a cycle. And if you do this at the right point, if you do it just at the right point, you will increase your energy.
So you're just lifting, okay? So at the right point, you just lift yourself higher. So now you have more falling time. And do the opposite.
And everybody will say, how are you getting the energy higher? And the reason is you're doing work over the cycle, and this is pumping energy. When Olympic gymnasts are
It's not really pumping it, but okay.
holding onto the bar, and they go round and round in circle, and you can see they've got rosin on their fingers, and there's clearly friction.
This is the spinning argument, and he doesn't really do it right. This is more about angular momentum.
They bend themselves at one point in the cycle to raise their center of gravity, and that way they pump energy into the system.
That part's true. All right, but
Turn
this
customers
terrible
into
example,
customers with
right?
the
I mean, just that was really a terrible video. Something as fundamental as important. What the hell happened to my mouth? Completely not working. Yeah, I can't just do nothing. Well, we'll slowly. I don't know what the hell is wrong. Probably a computer crashing issue. Yeah, the video still seems okay. Sorry, it's going to just take a little while to get this. Well, there it goes. I just have to get to stop recording. Yeah, get to the end of the video. There, I made it. Alright, so anyway, enough of a video and such. So, till the next time, and such, and so forth and whatnot. But yeah, just a mess out of a really important subject. I mean, mass and energy. That's the whole universe, right? Material things. Electrons, protons, and all the stuff they make. And motion. That's all there really is. Well, that's all there is. Really. If there were aliens and they did visit us, that's what they would tell you, is that, oh yeah, we're a million years ahead of you, and we finally listened to Gary, and yeah, so now we have the right answer. Yeah, it's really simple.